Hey everyone, this is going to be your homework assignment. So what I'm going to do here is I'm going to assign you guys some problems, and then I'm going to work them out with you. You're going to see a problem appear on your screen. Hit pause, work the problem out on your own, or get to a stopping point, or where you think you have the answer, or if you think you're confused or whatever. Stop wherever you got to stop, then resume the video, and then you can watch me do it. But try to do these on your own first. Don't do them with me, as I'm doing them. Okay, so here is your first problem. Given that f of x, I want you to find the slope of the tangent line at 2, 5. Find the slope of the tangent line for f of x at 2, 5. Okay, go ahead and work that out. Hit pause at this point, and when you're ready, unpause and come back. Okay, if you're still watching, or if you unpause at this point, you're going to see me go through this one with you guys. So here's what you need to understand. They're saying find the slope of the tangent line. That's kind of like a twofold question. What they're really saying is not only find the slope, but you have to do something first. The first thing that you're going to have to do is find the derivative. The derivative is going to give you an equation that allows you to find the slope at any point. So find the derivative and then evaluate it at f of x equals the f prime of 2, or x equals 2. Your limit definition, limit as h goes to 0, the f of x plus h minus the f of x, all of that over h. That is the formula that will give you the derivative. And then you can evaluate that derivative at 2, 5, but really you're just going to be plugging in the x equals 2. Okay, so I have to find the limit definition of the derivative for f of x to first get me to the slope. So limit as h goes to 0. Anywhere I see an x, I'm plugging in the f of x plus h. So I'm going to plug in an x plus h for that x. So it's going to be 2 parentheses instead of x, x plus h squared minus 3. All of that is f of x plus h. Now, minus, I'm going to use a bracket because now it says subtract f of x. That's the function. 2x squared minus 3. I want to use brackets so that I don't forget I'm subtracting 2 items because there's 2 parts to that function. All of that over h. Okay, so that's the application of the limit definition. Now this works in the same rhythm every single time. You're going to clean up the numerator algebraically. Things are going to cancel out. You're going to factor out an h, and then you can evaluate as h goes to 0. You can't put h goes to 0 because you're always going to have a divide by 0 error. You got to simplify algebraically first, reduce the h by factoring out h and canceling, then you can evaluate. Okay, so it's going to be 2 x plus h squared, x squared, 2xh plus h squared. I'm doing x plus h times x plus h and foiling in my head when I did that part. Bring down the minus 3, and now subtract that original function. I'm going to distribute that negative to both. It now becomes minus 2x squared, and when I go minus minus 3, it's going to become plus 3. All of that over h. Keep cleaning up the numerator. Well, the first thing I see is these negative 3 and the positive 3, they're going to cancel each other out. Limit as h goes to 0. I have to distribute the 2 to all 3 terms in the parentheses. 2x squared, and now it becomes 4xh plus 2h squared. I've already canceled out my 3's. Bring down your minus 2x squared. All of that over h. Okay, now you notice I have a 2x squared and a minus 2x squared. Those can go away. That process of things like canceling out always happens. Have an h and an h. I can factor an h in the numerator. So let me come over to this side. Limit as h goes to 0. Factor out an h. You would be left with a 4x. You would be left with a 2h over h. You have h over h. That reduces. You're left with the limit as h goes to 0. Notice I wrote limit h goes to 0 every time. 4x plus 2h. And now you can evaluate this as h goes to 0. So I'm going to plug in a 0 here. 2 times 0 is 0. 4x plus 0 is 4x. 4x is the derivative. So if f is the original function, f prime is the derivative 4x. The derivative is going to give you an equation, 4x, that will find the slope of the tangent line at any point. The slopes are always changing because that's a parabola. I want to know the slope at 2, 5. 2 is the x value I'm interested in. The 5 is not going to come into play. I just have to evaluate the derivative, f prime, at 2. 4 times x, 4 times 2 equals 8. So the derivative at 2 is 8. That means the slope of the tangent line at 2 is 8. That means the instantaneous rate of change at 2 is 8. The derivative is always 4x. The slope changes depending on where I'm at. If I wanted to know the slope at 3, I can now find the f prime of 3. I would get 12. 4 times 3 is 12. The slope would be 12. If I wanted to know the slope at 10, I could plug in. So it's advantageous here to find the equation of the derivative so that you can evaluate it if I were asking for multiple points. If I said to find the slope of the tangent at 2, 5, and then at x equals 4, and then at x equals 5, and then x equals 6, now you can rapid fire plug those x's into f prime. Let me show you another way I could have done this problem. The way I did it now, I kind of did two things at once. I found the derivative, then I evaluated the derivative. So I did the limit definition to find the derivative first. I could have evaluated and found at the same time if I'm only going to find one x value. Let me show you what I mean by that. I want to keep my formula up there in the top. I apologize for that blue being written over the orange. I don't think I can get rid of that without messing everything up. It's actually bothering me. I'm going to rewrite it. Okay, so what I'm going to do is evaluate the derivative at the same time I'm finding the limit definition of the derivative. So here's what I'm going to do. Let me rewrite it and start it the same way I did before. Limit as h goes to 0. 2, I plugged in x plus h because I'm doing the f of x plus h. So that's 2, x plus h squared minus 3, minus the original function, again with the bracket so that I don't forget I'm subtracting both of those terms, over h. That's how I started last time. And then I went through the limit process and I found f prime. Then I evaluated f prime. Let me show you a faster way. I want to know the derivative at 2. So I'm going to plug a 2 in for x and a 2 in for this other x. And this will evaluate the derivative using the limit definition. This is kind of like a little bit of a shortcut where you can evaluate at the same time. Limit as h goes to 0. 2 plus h squared, square the first, double the product, square the last. Bring down your minus 3. Okay, in these brackets, there's no x's, so I'm going to evaluate that. Order of operations, 2 squared, 4. 4 times 2, 8. 8 minus 3, 5. There's a negative outside, so it's a minus 5. All of that over h. Notice there's no x's because I'm evaluating for that x while I'm going, so I've gotten rid of the x variable. Okay, I have to distribute a 2 to each of these terms in the parentheses. Limit as h goes to 0. 2 times 4 is 8. Plus 2 times 4 is 8h. Plus 2 times h squared. And negative 3 minus 5, I'm going to combine them. I could have done that in the last step, minus 8. Just adding those two up. Over h. Look what happens. 8 and 8 go away. I have an h and an h that I can factor out. Let me come to the right side of the screen. Limit as h goes to 0. Factor out the h. 8 plus 2h, all of that over h. Cancel out the h's. See ya, see ya. Limit as h goes to 0. 8 plus 2h. And now that you don't have any x's, you can evaluate that. You can plug in this 0 for the h. 2 times 0, 0, plus 8. Same thing I had before, 8. This is the derivative evaluated because I put in an x to begin with. So what I really found was f prime of 2, and now I know it equals 8. All right, this technique, that would not be advantageous to use if I asked for multiple points, because I don't have an equation for f prime of x. So if I'm only doing 1 point, this might be faster. If I was doing multiple points, you want to have that f prime of x that we had the first time when we said 4x. This technique skips that step because it's evaluating at the same time, and it kind of hides that part from you. So that's up to you on how you guys want to do it. I would do it the way I did it the first time because it is very advantageous to have that formula for the derivative, not just the evaluation of the derivative. But in either case, I found the slope of the tangent line. Here's your next 3 problems. Simple directions, find the derivative using the limit definition. I'm going to write down the limit definition, and you're going to start working them out. And at any time while I'm writing this down, you can hit pause and then join back in, and I will go through these 3 questions. All right, if you're unpaused, here I go. Number 18, limit definition is up there in the top right in pink. Limit as h goes to 0. I see an x. I'm going to plug in an x plus h because I'm doing the f of x plus h. I'm doing the front half of that numerator. Minus 3. Minus, you're going to want to use brackets here. You're taking away the 7x minus 3, the entire function. All of that over h. Okay, same rhythm as every single time. Clean up the numerator. Things are going to cancel. Factor out an h, and then you can evaluate as h goes to 0. 7 times x is 7x. 7 times h is 7h. Bring down the minus 3. Distribute the negative, minus 7x. Distribute the negative, minus minus is plus 3. All over h. Still cleaning up the numerator, but look, negative 3 plus 3 goes away. 7x minus 7x goes away. And while I'm at it, I'm left with h over h that can now go away. Technically, that should be 2 steps, but I've already gotten rid of the other steps. You can't get rid of that h until you get rid of all the other stuff, which I did. So I'm left with a single answer. The limit is 7. That means the derivative is 7. That means f prime of x equals 7. Now this wasn't asked, but I'm going to throw this at you anyway. This said find the derivative. Done. If I were to ask you to evaluate the derivative, there's no x's next to that 7. So the f prime of 1 is 7. The f prime of 2 is 7. The f prime of 10 is 7. Because there's no x's to evaluate 1, 2, and 10. So in other words, the derivative is always 7. You want to know why? Graph that. 7x minus 3 is a linear function. It has a y-intercept of negative 3 and a slope of 7. If it's linear, the slope is never changing. The slope is always 7. The derivative is the slope. So no matter where you're at, the slope is always the same. It kind of makes sense. You should be able to recognize, hey, if this is a linear function, I know the derivative is just going to be 7, and you can double check yourself while you're going through your process. Okay, let's look at 19. So there's going to be a trick with the next one as well. The next problem is going to be a linear function also. Now, if you go off of what I just said, linear function slopes are always the same. So let's just take a little shortcut, and then I'm going to do it the long way with the limit definition as well. All right, so it's a linear function. I'm looking at 19. The slope is the number in front of the variable s, 2/3. So my derivative will always be 2/3. Okay, I'm going to ignore the s's. This came from your textbook. I'm just going to imagine that these were x's here. It doesn't matter what the variable is. But let's do the limit definition. If I didn't put x's, I would just have an s up here in the formula, but that's irrelevant. Limit as h goes to 0. 3 plus 2/3 x plus h, because I'm plugging in the x plus h, minus the original function, f of x, 3 plus 2/3. Don't be afraid to use those brackets so that you don't forget to distribute that negative over h. All right, 2/3 times x and 2/3 times h. Limit as h goes to 0. 3 plus 2/3 x plus 2/3 h minus, distribute the negative to both, minus 3 minus 2/3 x, all of that over h. Okay, look for things to cancel out. You got a -3, you got a +3, they're gone. You got a 2/3 x and a minus 2/3 x, they're gone. I skipped this step last time, but I'm going to write it down just in case you didn't catch what I was talking about. Now you're left with 2/3 h over h. Now you can cancel out the h's, and you're left with 2/3, just like I said was going to happen. It's a linear function. The slope never changes, so the derivative is always 2/3. Even if I didn't ask you to evaluate, the answer is always 2/3 for the derivative evaluated at any point. 21. '21 is a quadratic. It's not linear. So the derivative is going to have a variable in it because the derivative, the slope of the tangent line, is going to vary. X squared, I'm plugging in an x plus h for that x squared. Plus x, I'm plugging in an x plus h. Minus 3. Minus f of x, that's the quadratic. Use your brackets. All of that over h. Algebraically clean it up. Things will cancel out. Factor out an h, then evaluate. Limit as h goes to 0. X plus h squared. X plus h times x plus h. I've done this multiple times. Plus x plus h. Minus a 3. Distribute the negative to that trinomial. Minus x squared minus x. Minus a minus becomes plus 3 when I'm multiplying that negative or distributing it. All of that over h. Cancel things out. I have an x squared and a minus x squared that go away. I have a plus x and a minus x that are going to go away. I have a -3 and a plus 3 that are going to go away. Here's what I'm left with, just so it doesn't get too busy. 2xh plus h squared plus an h. That's it for the top. H in the bottom. I have a trinomial in the top where they all three have h's. I can factor out an h. So that is going to become limit as h goes to 0, factoring out the h. You're left with the 2x. You're left with 1h plus 1 over h. Cancel out your h's. Gone. I'm going to go ahead and evaluate on this same step. I'm going to plug in that 0 So I'm running out of space. I would prefer that you write down that one more limit as h goes to 0 of 2x plus h plus 1, then evaluate, but I'm running out of space. So I got 2x plus 1 because the h goes to 0. That is the derivative. That is f prime. So the derivative is going to be 2x plus 1. I didn't ask you to find the derivative at a specific point, so you have a formula to find the derivative at any point. So that's 21. Here's your next question. I'm going to cut off some of these directions. I cut these out of your book. The part with the graphing calculator, I'm not doing that. I want you to find the equation of the tangent line at that point. And I'm going to give you a couple seconds to think that through. If you're not knowing where to start, keep listening. If not, hit pause and go. Okay, if you don't know where to start, find the equation of the tangent line. That means you need to find the derivative. You then need to evaluate the derivative. That will give you the slope of the tangent line. From there, you're going to find the equation of the tangent line using your point slope formula. There's your hint. Pause if you want to continue. Okay, I have to find the derivative. I need to find the equation of the derivative. So I'm going to use the limit definition. X squared plus 3. I'm not writing the formula down. X plus h squared plus 3 minus f of x over h as it goes to 0. Clean it up. Limit as h goes to 0. Square the first, double the product, square the last. Bring down the plus 3. Distribute the negative. Minus x minus 3. That's why I use the bracket, so I didn't forget to do minus both of those. Over h. Cancel, factor, evaluate. X squared and x squared cancel each other out. Plus 3 and minus 3 cancel each other out. Limit as h goes to 0. 2xh plus h squared is what's left over h. Factor it. Limit as h goes to 0. Factor out an h. H comes out. You're left with 2x plus h. Over h. Cancel out. H and h go away. You're left with limit as h goes to 0 for 2x plus h. Evaluate it. Plug in that 0, and you're left with 2x. That is your equation for your derivative. That will give you the slope at any point. I am interested in the slope at -1, 4. So I need to find f prime of -1. 2 times x, 2 times -1, -2. That is my slope of my tangent line at -1, 4. That is my m in my y minus y1 equals m x minus x1 equation. So now I know that m is -2 because the slope of the tangent line is -2 because the derivative evaluated at -1 is -2. I know that sounds repetitive. Eventually it's going to sink in and I'll have to stop. I'll be able to stop saying it. Y minus y1. Here's your x1. Here's your y1. You got the slope of the tangent line at that point. I want the equation of the tangent line. Y minus y1 minus 4. Slope, we already figured that out. X minus a -1. Clean this up. Y minus 4 equals -2x. This would have been +1. I'm going to distribute that negative to a +1. I'm going to add 4 to both sides. Y equals -2x plus 2 is the equation of the tangent line. -2 is the slope of the tangent line. 2x is the derivative. Visually, here's what we did. If I were to graph x squared plus 3, It's a parabola. Shifted up 3. The point -1,4 lands on said parabola. That's that point. The equation of the tangent line is -2x plus 2. You found the equation of that green line. Its slope is -2. Done. Next question. I want to know if the derivative from the left and from the right at x equals 1, if they exist. Therefore, is that function differentiable at x equals 1? So you have to find the derivative from the left limit definition, the derivative from the right, and then compare them to each other. All right, so pause at this point, let you tinker around with that. When you're stuck or you're done or you're ready, come back. All right, I'm back. On this one, I am not going to use the limit definition. It's going to be too confusing to try to do that one, the limit definition. I mean, I could. Do I need to? I don't know. Like, I can rewrite this equation. The f of x, if that's absolute value, you first need to know the, or recall the definition of absolute value. Whatever was in there could have been positive. So I'm going to make it a piecewise function. It could have been a positive, or it could have been a negative. That could have been a positive number to start with. It could have been a negative number to start with. You can drop off those parentheses if you want. You can distribute that negative to both of those. So it's really going to be -x plus 1, just to make it visually easier to see. I guess my negative's not in the best spot. Let me slide that over as well. So if whatever was in there was negative, it would have been -x plus 1. Okay. It would have been positive when your x values were greater than or equal to 1. It would have been negative when your x values are less than 1. It would have been 0 when, well, I guess it would have been 0 with x. The inequality part's not important. It would have been 0 with if it's greater than 1. It doesn't matter. You could do your limit definition for these, but I'm not going to. I'm going to save some time. So I need to know the derivative, left-hand limit from the left, yeah. And then I need to know the derivative from the right. The reason why I'm not going to do that, because it takes too much time. I just mentioned twice that this was a, these are two linear functions. And linear functions have the same derivative everywhere. Like if you were to graph the absolute value of x minus 1, it's a v shifted to the right one. So I can go through my limit definitions, like maybe on the AP exam you would have to do this. I'm trying to hit home a concept here. The derivative from the left is the slope of those lines from the left of 1. The slope everywhere on the left of 1 at x equals 1 is always going to be -1. The derivative on the right of 1, x, those slopes are always going to be +1. The only way that this function can be differentiable at x equals 1 is if these two were the same value. If the derivative from the left and the derivative from the right were the same, like a limit approach. They're not the same. So this is not differentiable. Now, if you don't believe me, go ahead and apply the limit definition to the left and the limit definition from the right, and you'll see, like for instance, when you say the limit as h goes to 0. I'm doing the left, so I'm using the bottom one. So it's going to be negative x plus h plus 1. Then you're going to go minus negative x plus 1, all of that over h. You're going to see that's going to reduce down to negative 1 anyway. But I'm kind of just doing like a common sense approach here because I know it's absolute value. I know it's a v. I'm using the definition to describe the slopes are always going to be negative 1 and positive 1. And if it's differentiable, they should be the same. Like I said in the class, if you recall, there is a sharp corner at x equals 1. You cannot take the derivative at a sharp corner. So just another little visual that kind of goes along with this one, which may be helpful for you guys. We're going to get into graphing derivatives at one point. And let me just mention something here. If I were to graph the derivative, this is f of x. If I were to graph the derivative, f prime of x, at 1, the derivative to the left of x equals 1 is always the same thing. It's always negative 1. The derivative on the right of 1 is always the same thing. It's always positive 1. There is a point of discontinuity at 0. So I have an open circle and an open circle because I can't take the derivative at 0. And that's why I was saying in the beginning, it doesn't matter where you put the or equals to, because for the derivative, the jump discontinuity anyway. You cannot evaluate the derivative at 1. So the f prime of 2 is 1. The f prime of 3 is 1. Oh, I messed up. I don't know why I put those at 0. I meant to put them at that green 1. Like this. So x equals 1 is where it's not differentiable, so there's that jump. This has a value of 1. That's what messed me up. I was thinking to put the scale on and then I accidentally circled the wrong spot. Sorry about that. The derivative is 1. So at x equals 1, if it's asking you for the derivative at 2, it's 1. The derivative at 3 is 1. The derivative at 4 is 1. But you can't find the derivative at 1. So it jumps down to the other one if you're going to the left of 1. There's still a point of discontinuity. I drew it on the axis, not slided over at 1. Sorry. Okay, last one. Determine whether that function is differentiable at x equals 2. Using the limit definition of the derivative, you're going to have to find the derivative to the left of 2, the derivative to the right of 2, compare those two answers to each other. If they're the same, it's differentiable. If not, it's not. All right, let me go through that process if you're ready. If not, hit pause again. So derivative from the left versus the derivative from the right. I have a function that goes from a parabola to a line. And I want to know if there's a smooth transition from the parabola to the line. Limit as h goes to 0. X squared, I'm plugging in x plus h, squared plus 1, minus the original function, brackets, over h. That's the limit definition of the derivative to the left of 2 using the parabola. Limit as h goes to 0. Square the first, double the product, square the last. That's the binomial squared. Bring down the plus 1, distribute the negative to the brackets. Over h. X squareds cancel out. 1s cancel out. factor out an h. H's cancel out. The answer would be left. There's no x's to no h's to plug in. You're left with a 2x. So the derivative from the left of that parabola is 2x. Same thing on the right. But I'm using 4x minus 3 this time. 4x plus h minus f of x distribute 4 times x, 4 times h, minus a 3, distribute the negative, (4x) cancels out with 4x. 3 cancels with negative 3. Skipping a step to save time, h's would then cancel out if you were to write one more step. The limit as h goes to 0 will equal 4. So the derivative from the right is 4. The derivative from the left is 2x. Therefore, it is not differentiable, and it's not differentiable because their derivatives are not the same. Ooh, pause on that thought. Think about this. I did not evaluate the 2, and this is where a common mistake would be. A lot of people will see the 2x and the 4 and they'll stop. Okay. You found f prime of x, 2x. You found f prime of x equals 4. But what you did not do, or I did not do, I misled you into it on purpose, is you do not evaluate that derivative at 2. So what we need to do is actually find the derivative at 2. On the right, the f prime of 2 equals 4 because there's no x's to plug in. On the left, the f prime of 2 is 2 times 2 equals 4. Oh, they are the same because you have to evaluate the derivative. Remember, the limit definition gives you a formula, 2x, for the derivative at any point. Evaluate that derivative, you got a 4. The limit definition on the right gave you a formula, 4. There was no variables. Hey, check this out. That's a linear function. A linear function is always the slope, 4 and 4. A parabola has a different slope at a different point. That's why it varied. It had a variable, 2x. So you evaluate the derivative. So it's a little bit one kind of more step than that last problem. All right, so this one is differentiable because, I'm not writing this down, the derivative from the left and the right are the same after you evaluate them. That's the key part on this problem. And if you were to graph this piecewise function, you would have a parabola transitioning to a line on a smooth transition instead of it being a cusp or a corner. All right, that is your homework assignment. I know that was only a handful of problems, but that really covers everything that we talked about in the beginning with derivatives. It gives you a little bit more extra practice. So I hope you found all those things helpful. If not, you can rewatch that as many times until your heart's content. See you later.